Hello and welcome to this deep dive into one of the most revolutionary technologies of our time, quantum computing. In this presentation, we will explore what quantum computing is, how it works, and most importantly, how it will transform the way we develop software. From the underlying physics to real world coding languages, this is your front row seat to the future of programming and problem solving. Let's begin this fascinating journey. To understand how quantum computing changes everything, let's first understand what it is. Quantum computing is based on quantum mechanics, a branch of physics that explains how the tiniest particles in the universe behave. Instead of bits like 0 or 1, quantum computers use qubits, quantum bits that can represent both 0 and 1 at the same time. This means a quantum computer can process a massive number of combinations simultaneously. Superposition, entanglement, and interference aren't just fancy terms, they are the key to quantum's power. Think of it like this: while a classical computer is like a flashlight exploring one path at a time, a quantum computer is like sunlight illuminating all possible paths at once. Let's compare classical and quantum computers side by side. First, the building blocks. Classical computers use bits either 0 or 1. Quantum computers use qubits, which can be in both states at once. This allows quantum computers to operate with a level of parallelism that classical systems simply can't match. That's why they hold promise for solving problems that would take classical supercomputers centuries. For instance, searching large unstructured databases, cracking modern encryption, or simulating molecules in chemistry. These are all extremely difficult, or even impossible for classical systems, but solvable with quantum methods. So, while today's classical algorithms are deterministic and step by step, quantum algorithms are probabilistic, parallel, and mind blending efficient. Now let's unpack the three core principles that give quantum computers their edge. First, superposition. Imagine flipping a coin. It's either heads or tail. But in quantum terms, the coin is spinning in the air, representing both heads and tails at once. That's superposition. A qubit can hold multiple values at once, allowing massive parallel processing. Entanglement, a mysterious quantum link between particles. If two qubits are entangled, changing one instantly affects the other, even if they are miles apart. This interconnectivity allows quantum computers to coordinate calculations across qubits with near magical precision. Finally, interface lets quantum computers cancel out incorrect answers and amplify the right ones, guiding computers towards the correct solution. These three ideas, superposition, entanglement, and interference, form the bedrock of quantum software design. So, how does all this theory translate into actual software? Enter quantum algorithms. Shor's algorithm, developed in the 1990s, made headlines by showing that quantum computers could break RSA encryption, a foundation of online security. That was a wake up call. Then there's Groover's algorithm, which can search unsorted databases in far fewer steps than classical searches methods, a massive improvement in efficiency. Even more exciting is the potential of quantum machine learning or QML. By leveraging quantum speedups, QML could redefine how we train and deploy AI models, especially for big data problems. These are just the beginning. More quantum algorithms are being researched every day, covering everything from optimization to drug design. What does all of this mean for software developers? It means we need to reimagine how we code. Instead of writing code with loops and conditions, quantum programming involves building quantum circuits, networks of gates that manipulate qubits. Developers will need to understand quantum logic, build error correcting mechanisms, and think probabilistically instead of deterministically. Tools like Qiskit, SARQ, and QSharp are already available, allowing developers to experiment on real quantum hardware via the cloud. The shift is as dramatic as the move from punch cards to high level languages, but this time we are not just changing syntax, we are changing the very foundation of computing. Here's a snapshot of the main quantum programming languages driving this transformation. Qiskit, developed by IBM, is a open source and Python based, making it beginner friendly. It allows us to create quantum circuits and run them on IBM's quantum machines. QSharp from Microsoft is designed for scalable quantum programs and integrates with Visual Studio. SARQ by Google is focused on algorithms that run on near-term quantum hardware. what we call NISQ or noisy intermediate scale quantum devices. These tools aren't just experimental, they are the beginnings of a new software development ecosystem. But let's be realistic, quantum computing is not without serious challenges. Qubits are extremely delicate, they decohere or lose their quantum state very quickly. Building stable systems requires ultra-cooled environments, sometimes near absolute zero. Error rates are still high, and scaling qubits beyond a few hundred remains a major hurdle. We also lack mature debugging tools and widespread developer expertise. So, while the potential is huge, we are still in the early stages. We are experimenting, learning, and gradually improving. The next decade will be critical in overcoming these barriers. Despite these obstacles, the road ahead is bright. Major companies like IBM, Google, Microsoft, and Amazon are offering cloud based access to quantum systems. Developers can already run real quantum programs on live machines through platforms like IBM Quantum Experience and Amazon Beckett. In the near future, hybrid systems where classical and quantum computers work together will become the norm. And by 2035 or even earlier, we may see quantum breakthroughs in industries like medicine, aerospace, cryptography, and logistics. As we move forward, we are not just building faster machines, we are redefining what it means to compute. To conclude, quantum computing is not here to replace classical computing, it's here to complement it. In some tasks like gaming or text editing, classical computers will always be better, but for simulating molecules, solving optimization problems, or breaking complex cryptography, quantum computing will reign supreme. For software developers, this is both a challenge and opportunity. Those who start learning today will be the pioneers of tomorrow's breakthroughs. The tools are available, the time is now. Because in the world of quantum, it's not question of if, it's a question of when.